Hello, hello. This is QMG, the quantum mechanics guy, bringing you another episode on the wonderful world of quantum mechanics. So here's the big question. What role do quantum interpretations play in quantum mechanics? Why do we need the many world interpretation of quantum mechanics? Why do we need Bohm's interpretation of quantum mechanics? Are we supposed to just shut up and calculate without questioning the foundations of quantum mechanics? Are we not supposed to think deeply about quantum theory? Why are there so many ways of looking at quantum mechanics that seem so strange? What is quantum physics really about? Today, with the help of a wonderful professor, we will discuss some of these questions, but don't think that I will agree with the philosopher that will be speaking, because I will show you that science is not about finding what there is, but about finding what could be wrong with something. The goal of quantum physics is to find conditions where quantum physics could fail, using interpretations as practical guides. Quantum interpretations are maps that guide the ships to places where the unexpected is. So, let us begin.
You've written or thought a lot about quantum mechanics, and a lot of people see it as the most as like giving the most accurate.
By the way, I love the accent of the moderator.
Compared to other scientific theories at the moment, but some of your latest work looks at how quantum theory is actually missing a lot. Would you be able to explain this?
Right, so there's no doubt, and no one can dispute, that there's a mathematical formalism that we know how to derive predictions, and those predictions can be accurate to.
That's right. Quantum mechanics is the most successful theory in human history, and there have been attempts to try to find it wrong, but nothing has been found wrong. So we agree.
Well, the theory is, what the physical theory is more than just a mathematical formalism with some rules. It should specify a physical ontology. It should tell me what exists in the physical.
Well, that's where we differ, right? No, okay, all right. A physical theory should be provisionally showing something that seems to be correct, given some conditions, but it could be wrong in other conditions, and science is about trying to find those conditions where it could be wrong. This is very confusing, I understand, to many people, but basically, as Richard Feynman said it very clearly in his lectures, first we try to find the wrong laws, and little by little we try to find the right ones, right? But it's not about trying to find what there is, as if what there is set on stones, right?
Particles, fields, is there space-time? Tell me about those things, and then specify some laws about how they behave, or tell me how they behave. And the problem is that there is standard quantum, what's taught as quantum theory isn't a theory in that sense. It's just the formalism. And then what people...
Okay, right. So far, we differ in the meaning of a theory. For him, a theory is something that tries to say what there is. But but a scientific theory, from the point of view of a scientist, a professional scientist, is more instrumental the way in which empiricism is looked at, right? the data that you obtain is something that was obtained by some process, but it's just an approximation to something going on out there.
Interpreting quantum theory, which sounds like a fun thing to do. You say, well, I have a theory, it's an interpretation. What's called interpreting quantum theory is really the development of precise physical theories that make the same predictions or nearly the same predictions that you get out of this standard mathematical recipe.
Okay, so he's clearly saying, speaking about interpretations, no, okay, the point of interpretations of quantum mechanics is to try to find something wrong with quantum mechanics under some conditions. It is true that interpretations of quantum mechanics try to make sense of the quantum world, but they also attempt to falsify the theory. And I know it is paradoxical, but even Richard Feynman in his lectures emphasized this point. Even Richard Feynman was aware that saying that what we have right now as science is not completely correct seems paradoxical, right? Because it seems like you have something that works. Why cannot, as a scientist, why can't you say that's what it is? Okay, and that is not the goal of science. Okay, the goal of science is improving it more and more.
And so this, to me, clears up a kind of funny question. They say, oh, a physicist would say, well, I've got quantum theory. What do I need interpretation for? Let the philosophers do the interpreting, whatever that is. And that's because the language is misleading them. No, you don't have a theory. You have a predictive recipe. And what we want, as a physicist, what you should want is
Well, it is true that physicists are see interpretations of quantum mechanics as something futile, given that the theory has been correct in every attempt. But it is not the goal of science. Science is not about conformity, right? It's about trying to find what might be wrong with that theory under certain conditions.
So does that mean that actually quantum mechanics is a lot stronger in its predictions than the...
A lot stronger in its predictions. Okay. Don't get the question of the moderator.
audience thinks, or does it mean that they're not there yet and they still need to work towards having the status of the theory?
Well, there are different approaches that people have been working on. This is a very minority group.
By the way, I love the setting in the back. Okay, it's I wish I could do it in the forest or in a park. That way I don't have to be using artificial light. I'm sorry.
Foundations of physics. So there's a whole approach that goes back to 1925.
Okay, he's talking about foundations of physics. By the way, I work on foundations of physics. And as you may know, I recently submitted a manuscript for publication called A Delayed Choice Quantum Eraser Experiment with an IBM Quantum Computer, where I present an experiment with results which gives a different interpretation, right? It allows to make a fundamental interpretation about quantum mechanics that is not obvious. Okay, so I just wanted to throw that in there.
Other approaches that are called objective collapse theories, some other physicists, particularly work on versions of objective collapse theories. And these are just different theories, and they all make the same predictions insofar as they've been tested.
Right, all these interpretations make the same predictions. But here's the lesson from my paper, okay? Let's do first a clear experiment that we can try to interpret, not the other way around. A more clear experiment allows more clear interpretations, right? There are many interpretations of quantum mechanics, but if you always try to start with clear experiments, that's going to translate into clear language to describe those particular situations, and those interpretations will be would be less vague.
Can't go to a lab and say which of these approaches is right, even though in principle sometimes these different approaches make slightly different predictions. You have to think very hard about how you could actually test it.
And what the
Exactly. You don't have that problem if you actually start with experiments and then you start interpreting a little more, right? Of course, some interpretations allow to make experiments, right? It's sort of inspired to start to do it there, but to go into that direction. But it's good to have something tangible to back up your interpretation. That way, your interpretation is not broad and vague and quixotic.
does quantum tell us about physical reality?
Well, that's what's interesting, is that these different approaches would give you different answers. So if I say, well, I think it's the pilot wave approach is correct, I'm going to say, well, it tells me that the quantum mechanical wave function is not a complete physical description.
Right, so he's talking about Bohm's interpretation at this point, and I should mention, okay, I should bring this, that the pilot wave theory was refined by Bohm because he expected the quantum theory to fail under certain conditions that he specified. Oh, what was that? Oh, so something here. So it was not supposed to be about an ontological theory. It came out that way eventually. Eventually, quantum theory was correct, so it just stays as an interpretation. But Bohm, what he's talking about, the interpretation that he's mentioning right now, was supposed to be incorrect under certain conditions. It wasn't, so it just stay as a theory. So it was not an ontological theory as he's trying to present it.
Maybe the world is deterministic, and if I take an objective collapse theory, I'm going to say that tells me the world is fundamentally indeterministic. And so there's no single answer. The one thing we know for sure is that there's a kind of non-locality. This comes from the theorem of John Bell.
All right, okay, and he's not presenting the whole story here, and a lot of people don't present the whole story behind John Bell. John Bell provided originally a falsifiable interpretation of quantum mechanics. He tried to interpret quantum information as definite outcomes from their sources, basically hidden variables, as Einstein called it. He designed an experiment that could show that his theory could be wrong. And in fact, John Bell's theory was wrong. He was surprised. Nobody talks about that very much. And so it turns out that quantum mechanics is a non-local theory, but it was contrary to the expectations, to the initial interpretation of John Bell. Okay, so what he's talking about right here, that locality, the reason John Bell, we talk about John Bell's theorem, is precisely because, he found something that could be wrong. It was wrong, but still, the mistake, quote unquote, or the error, or what was wrong with his original interpretation was worth it, was worth the try. So we know something about quantum mechanics that is worth knowing. Okay, that is non-locality as he defined it, and as you can see, the purpose of science is to find something wrong, and even those things that are wrong sort of allows you to make a contribution to science.
Which doesn't depend on the interpretation. John Bell proved that just certain results.
Yeah, it doesn't depend on the interpretation, but his original interpretation failed. That's what he's not talking about.
Lab cannot be reproduced in a theory that is local in a certain well-defined sense. So there has to be some non-locality.
Where do you stand amongst these theories?
I mean, I have a slight, but this is just my preference. My aesthetic sense is that the pilot wave approach seems more natural than the objective collapse approach.
Sure, sure. You can pick whatever works for you, but there seems to be among many amongst most professors in academia gravitate towards the original orthodox Copenhagen interpretation. He's going to mention that a little later. So one may say that it is the most simple one, right? So in terms of he's talking about aesthetic preference. Well, it seems like there are some that are actually more simple, and my judgment for that is the number of people that tend to gravitate towards those interpretations. The Copenhagen interpretation seems to be simple enough, okay? And it seems like the other interpretations don't seem to be necessary, right? Certainly, you can have an aesthetic preference for one over the other, but certainly we could make the argument based on numbers that there are some interpretations that seem to be more simple.
More unnatural, but I wouldn't, give a lot of attention to my aesthetic preferences here. They're both very serious. They're trying to write the theory down in completely precise mathematics.
Let's move forward a little. Let's move forward here because he's going to get to the Copenhagen interpretation, precisely what I was talking about right now. So he actually makes some comments about that, bring Schrodinger cats and everything.
Well, the Schrodinger cat thought experiment, when Schrodinger wrote it down, had a very serious point.
And I'm sure you have heard 1,000 times about Schrodinger's cat, okay? So he's going to talk about it, and that comes from the Copenhagen interpretation.
The point was that the understanding of quantum mechanics that Bohr and Heisenberg had produced, which goes by the name of Copenhagen interpretation, was completely unacceptable because it had this consequence that a cat could end up neither alive or dead. And Schrodinger said, that's ridiculous, right? That tells me you made a mistake, Bohr.
Okay, sure, you could say that that's what Schrodinger was doing. But Schrodinger was, you could say, one of the first ones to point out something strange about quantum mechanics, specifically about the Copenhagen interpretation, right? But notice how Schrodinger presents a simple, non-disprovable experiment, right? If you're familiar with the experiment, well, basically you have a cat in a box and you don't know whether the cat is alive or dead. If you don't look at a cat, then there is no way of knowing what is going on from an instrumental point of view inside the box, right? So you can say in this way that Schrodinger was not thinking like a scientist, right? His concerns were not about science, were not about trying to create an experiment that is falsifiable. It was sort of a problem with the interpretation itself. There was something that didn't seem to be correct, but he was not thinking like a scientist.
Right, that's the mistake, Heisenberg. Go back and think again. And so the example had a very serious purpose. The purpose wasn't to convince you that there are cats that are neither dead or alive. That was supposed to be the absurd consequence.
All right, so let's move forward here. And I think right here he starts speaking about something very moving to the core.
And then when it came to the United States, all of this Bohrian kind of hard to understand mystical philosophy got kind of thrown away. And then it came shut and calculate. So they said, well, just don't ask us questions like, what's really going on?
All right, shut up and calculate. That's a very typical expression. Okay, so pay attention to this one.
Just, we have a thing that you can use to make good predictions. Just use it to make the predictions. And don't ask. And that, when I studied physics as an undergraduate, that happened to me in my first quantum mechanics course. I put up my hand and asked the physics professor well, is it like this? And his answer was, no, you can't think of it that way. But then he didn't go on to say, here's how you think of it.
All right, okay, so let me explain this one. Okay, the shut up and calculate is not meant to discourage anyone from interpreting quantum mechanics. Okay, it is means to inspire you to want to find falsifiable new interpretations that could show that the foundations of quantum mechanics are wrong, because that is the goal of science, right? By shutting up and calculating, right? It is true that there is no time in the classroom to satisfy the inquiries of every student, but that does not imply that students should not find new ways to test many aspects of quantum mechanics. So I disagree with his with his anecdotal evidence.
Like, don't think of it, right? It's just calculate the numbers. And so this shut up and, has become known. It's not quite clear who started this. This shut up and calculate.
Oh, that was started by David Mermin. Okay, and I'm working on a video on him because he tried to inspire people to create falsifiable experiments. Okay.
And that's a practical point of view if all you care about is making predictions. But if you care about what the world really is, not about building bridges or microchips, but if you're just curious, what's really going on, shut up and calculate.
Oh, wait. No. Shut up and calculate gets you everywhere if you find an interpretation that is falsifiable, right? That's how we get somewhere. Okay, so he's misinterpreting shut up and calculate, and I don't blame him because there's so many people that think that shut up and calculate is just some way to dismiss interpreting whatsoever. No, it's not that. Okay.
And so the physics textbooks are all written by people who never studied these questions because they were told not to ask them and not to think about them. They were
No, they were encouraged to learn about the subject and then question what might be wrong with it.
But if a theory helps you make predictions, shouldn't it also, like, doesn't it take what the world really is or what reality is?
Great question from the moderator. Okay, and let me tell you, I love the way he responds. Okay, because I think his example really helps to clarify much of this conversation.
People knew for thousands of years ago that aspirin will actually have medical use to make your head ache. They knew that empirically. They didn't have a clue, even long into the 20th century, how it works. They knew you took the bark of a certain tree and you chewed it or whatever, and your headache went away. Now,
right. Wonderful example. But it is by doing falsifiable experiments guided by appropriate interpretations that one can determine the mechanism that makes something work, right? In the example of aspirin, somebody had to do an experiment in order to find exactly what is the substance that cures a headache, right? So first, they did something, you can say it was wrong, and little by little, they get to something more and more specific, something more specific, right?
All you care about is getting rid of your headache. You're happy. You don't care how it works. So you can have some.
Again, finding how it works is achieved by doing falsifiable experiments, not just by sitting down and trying to create some pragmatic interpretation of the situation, right? And if one tries to create an interpretation, well, what's the experiment backing that up?
Thing that tells you very effectively, practically what to do, and not have a clue why it works. You may know that it works, but not have a clue how it works. Yes, that's exactly what's happening in quantum theory. We have a very effective mathematical recipe for grinding out predictions. and those predictions are really accurate. So there's something in that recipe that reflects the real world. But exactly what reflects the real world and how?
Okay, that is right. People in science should design, well, in quantum physics specifically, we need to design more experiments. At least thought experiments, not come up with quixotic interpretations to fit your taste. So you can say that there are many interpretations of quantum mechanics out of frustration with the theory, but the solution is very simple. Just stick to an experiment.
You can stare at that mathematics from morning till night, and the mathematics won't tell you. You need a physical theory.
So the way you
All right, so let's move on to a little bit forward. Right here.
happen in the academic environment, in particularly in what.
So right before this one, they were talking about powers between departments.
Physicists are doing with quantum now.
What I really want to happen, what I'm working hard right now, practically,
So this is what he wants.
is simply to have foundations of physics recognized.
Bingo. Okay, so his whole drive for this is to have a recognition, right?
That's it. It's something that some people can devote their lives to. And if you're a physicist who doesn't care about it and you just want to make the predictions, or you just want to run the experiment,
All right.
but you,
Okay, all right. Look, it is very simple to have foundations of physics recognized if you design experiments that test the boundaries of quantum mechanics. Specifically, if you run the experiments that give particular interpretations that you want to push forward, right? Simple.
say there are these people who are interested in this question, and they're doing also a serious undertaking and have it recognized institutionally.
Right. I recognize that there are philosophers, okay? So you want recognition of foundations of physics and specifically philosophers of foundations of physics. I recognize that there are philosophers that are pushing science forward by offering interpretations to experiments that at least that are less quixotic than the other interpretations. If you check out my paper, Delayed Choice Quantum Erasers with the IBM quantum computer, you'll see that I actually cite a philosopher who articulated the issue of retrocausation better than anybody else. He did a wonderful job. And in fact, he's a quantum physicist for his work on the foundations of quantum mechanics. And as you can see, his interpretation help me, okay, have a citation in my paper for the particular experiment that I'm presenting. Okay, so you want recognition, stick to experiments, and you'll get recognition.
It would be nice if every student who learned quantum mechanics at least got a 3-page accurate description of the situation, right? If you really want to understand the foundations, then you have to have class in foundations. Sometimes physicists have this idea as they have a physics PhD, they must know all these answers. And but then you have to ask, well, where did you learn it? It wasn't in your textbooks. You never learned foundations.
Look, of course, it is true. A lot of people a lot of physicists learn about foundations of physics on their own after we learn something about quantum mechanics in the classroom. I can tell you, I didn't learn about different interpretations of quantum mechanics in the classroom. I had to read a bunch of books on my own. You can say that I learned quantum computing by myself, and I create my own interpretations based on my own knowledge of quantum mechanics, but that is the point, right? Of learning quantum mechanics in the classroom is to make you independent so that you can actually find information on your own.
You never took a course in it. You never read a chapter about it. You never read a book about it. Why do you think you know it? All I really want people to do is to recognize serious work and there's serious people. Some people in physics department, some people in math department.
Yeah, well, I'm going to say this. If it is serious, show me a falsifiable experiment that you designed that could be built with current technology, right? Simple.
Philosophy departments working on a common project, and it's a legitimate project.
Thank you so much.
Right. So, what do we learn from this? Okay. Science is about trying to find new ways of looking at things. It is certainly useful to have interpretations of quantum mechanics because we want to find simple ways of looking at things. But ultimately, what we hold to be true is provisionally true. It could be wrong under different conditions, and we should be looking for ways to disprove that actively. And we should be able to think of experiments that can be created with current technology in order to be able to find what could be wrong with that theory. No theory is 100% correct. It's not about verifying that theory over and over again with some new interpretations. It's about trying to show how that theory is wrong by shutting up and calculating. As simple as that. Well, this was QMG, and thank you for being here. And as always, for those about to quantum, we salute you.